Have you ever wanted two microcontrollers to communicate wirelessly over a long distance without using Wi-Fi or Bluetooth? In this video, I am going to show you exactly how to do that using the popular nRF24L01 2.4 GHz wireless transceiver module. One of the best things about the nRF module is that it is not limited to a specific microcontroller. You can use two Arduino UNOs, two ESP8266 boards, two ESP32 boards, or even different microcontrollers together. In this tutorial, I have intentionally chosen two different microcontrollers, an Arduino UNO and an ESP8266 NodeMCU, to demonstrate that the nRF24L01 can easily establish reliable communication between different platforms. We will begin with a very simple example, where the Arduino UNO wirelessly sends a hello world message to the ESP8266. So let's get started. We will require the following components for this project: Arduino UNO, ESP8266, SSD1306 OLED display, nRF module, jumper wires, and breadboard. Before we begin wiring the project, let's take a quick look at the nRF module. The nRF is a low-cost 2.4 GHz ISM band wireless transceiver developed by Nordic Semiconductor. Unlike simple RF transmitter and receiver modules, the nRF can both transmit and receive data, making it ideal for two-way wireless communication. It communicates with microcontrollers using the SPI protocol and support data rates of 250 kilobyte per second, 1 MB per second, and 2 MB per second. Lower data rates provide better communication range, while higher data rates offer faster data transfer. One of the biggest advantages of this module is its very low power consumption, making it suitable for battery-powered IoT devices, wireless sensor networks, home automation system, robotics, and industrial monitoring applications. The module also includes useful built-in features such as auto acknowledgement, CRC error checking, automatic retransmission, multiple communication channels, and support for multiple receiving pipes, making wireless communication both reliable and efficient. Although the nRF operates at 3.3 volts, many beginners experience problems because the module is very sensitive to power supply fluctuations. To solve this issue, we use an nRF breakout adapter with an onboard 3.3 volt voltage regulator. The breakout board also allows us to safely power the module from a 5-volt supply. When using boards like the Arduino UNO, the onboard regulator converts the 5-volt input into a stable 3.3 volt output required by the nRF module. Another important advantage of the breakout board is that the addition of filtering capacitors. These capacitors help eliminate voltage drops and electrical noise that can cause communication failures, random disconnection, or the well-known radio hardware not detected error. If you are using an Arduino UNO, I highly recommend using this breakout adapter because it provides a more stable power supply and improves communication reliability. For boards like ESP8266, NodeMCU, or ESP32, which already operates at 3.3 volts, you can connect the module directly. However, the breakout adapter can still be used if you prefer its improved mechanical support and additional power filtering. Overall, using the breakout adapter is a simple upgrade that significantly improves the stability and reliability of nRF-based project, especially when transmitting data over long distance or operating in an electrical noisy environment. Now that we have learned about the nRF module and the breakout adapter, let's assemble them together. Take the nRF module and carefully align its 8 pins with the socket on the breakout adapter. Make sure the pins are properly aligned before pressing the module into the socket. Gently push the module down until it is firmly seated. Avoid applying excessive force, as bending the pins can damage the module or cause poor electrical contact. Once installed, the breakout adapter provides a stable and reliable connection while supplying the nRF with the regulated 3.3 volt power. Now let's wire the transmitter circuit using the Arduino UNO and the nRF module. If you are using the breakout adapter, connect its 5 volt input to the Arduino 5 volt pin, as the onboard regulator will provide a stable 3.3 volt supply to the nRF module. If you are using the nRF module without the adapter, connect its VCC pin directly to the Arduino 3.3 volt pin. In either case, make sure the module is never powered directly with 5 volt. Now complete the remaining connection as follows. Connect the CE pin to digital pin 9. Connect the CSN pin to digital pin 10. Connect the SCK pin to digital pin 13. Connect the MOSI pin to digital pin 11. Connect the MISO pin to digital pin 12. These SPI connections allow the Arduino UNO to communicate with the nRF module and transmit data wirelessly to the receiver. Since the ESP8266 operates at 3.3 volts, we can power the nRF module directly from the NodeMCU 3.3 volt pin. If you are using the breakout adapter, simply connect its power input according to the adapter specification, while keeping the logic connection the same. Now make the following connection. Connect the ground pin of the nRF module to the ground pin of the ESP8266. Connect the CE pin to D4 pin. Connect the CSN pin to digital pin 8. Connect the SCK pin to D5. Connect the MOSI pin to D7. Connect the MISO pin to D6. These SPI connections allow the ESP8266 to communicate with the nRF module and receive data wirelessly from the Arduino UNO. Before uploading the code, we first need to install the required libraries. The SPI library comes pre-installed with the Arduino IDE, while the nRF header file is included with the RF24 library, so no additional installation is required. The code begins by including the SPI nRF24L01 and RF24 libraries, which enable communication between the Arduino and the nRF24L01 module by specifying the CE and CSN pins connected to the module. We also define a communication address that acts like a unique wireless channel. Both the transmitter and receiver must use the same address to communicate successfully. Inside the setup function, serial communication is initialized, so we can monitor transmission status through the serial monitor. The radio.begin function initializes the nRF24L01 module, while the set PA level set the transmission power and set data configure the communication speed. In this project, we use RF24 PA low for stable short-range communication and 250 kb per second because it provides the best range and reliability. The open writing pipe function specifies the destination address for the transmitted data, and stop listening switches the nRF24L01 into transmit mode. Inside the loop function, a character array containing the message hello is created and sent wirelessly using the radio.write function. This function returns either true or false, indicating whether the receiver successfully acknowledged the packet. Based on this result, the serial monitor display either sent or failed. Finally, a 1 second delay is added before repeating the process, causing the Arduino to transmit the hello message continuously every second. Since we have already discussed the common nRF24L01 function while explaining the transmitter code, we will focus only on the new part of the receiver program. The receiver code includes two additional libraries, Wire and Adafruit SSD1306, which are required for communicating with the OLED display over the I2C interface. An OLED display object is then created by specifying the display width, height, and I2C communication. Inside the setup function, the OLED display is initialized using the display.begin function. If the display is not detected, the program stops execution to prevent further errors. The display is then cleared so that it starts with a blank screen before showing any received data. Unlike the transmitter, the receiver opens reading pipe using radio.open reading pipe and then calls radio.start listening, which places the nRF module into a receive mode and continuously wait for incoming wireless data. Inside the loop function, the program continuously checks for incoming data using radio.available. When a packet is received, it is stored in a character array using the radio.read function. The received message is first printed on the serial monitor for debugging and verification. After that, the OLED display is cleared, the text size and color are configured, and the received message is displayed on the screen. This process repeats continuously, allowing the ESP8266 to receive and display every message sent wirelessly by the Arduino UNO in real time. Now that we have completed the hardware connections and uploaded the transmitter and receiver programs, it's time to test our wireless communication. Here we have Arduino UNO transmitter. As soon as it power up, it continuously sends the message hello wirelessly through the nRF24L01 module every second. Now let's move to the ESP8266 receiver. This board continuously listens for incoming data from the transmitter. Whenever a packet is received, the message is displayed on both the serial monitor and the OLED display. Before turning on the transmitter, let's first power up the receiver. As you can see, the receiver is running, but it is not displaying any message. That's because the transmitter is currently turned off, so there is no wireless data being sent. Now I will turn on the Arduino UNO transmitter. As soon as it starts transmitting the hello message through the nRF24L01 module, ESP8266 receiver immediately detects the incoming packet. You can see the hello message appearing on the OLED display. This demonstrates that the receiver continuously listens for incoming data, and whenever the transmitter becomes active, it automatically receives and displays the transmitted message without requiring any additional configuration. And that's it. We have successfully established wireless communication between Arduino UNO and ESP8266 NodeMCU using the nRF24L01 transceiver modules. If you found this video helpful, please give it a thumbs up, subscribe to the channel and press the notification bell so you don't miss the next part of this series. If you have any questions or suggestions, let me know in the comments below. Thanks for watching and I will see you in the next video.